Hello everyone. In the previous class, we have discussed about the capacitance and the factors that affects capacitance. We have also learned that capacitance of a conductor is the ratio of charge to the potential. So, the formula for the capacitance is C equals Q by V. Now, we will find the capacitance of a spherical charged conductor. So, for that, it is the charged shell, or you can say it is a conducting sphere. If I will provide a charge Q on it, then it will uniformly distribute over its surface. Let the amount of charge on the surface is Q. This is the center, and let me take the radius of this shell is A. So, to find the capacitance of this spherical shell or conducting sphere, we need two things. The first one is the charge that is known to us, that is Q, and the second one, what is the potential. So we can easily find out the potential of this cell, as we know that the potential on the surface of a cell is K times the charge divided by radius. So this is the potential, and this potential will be same across all the points if it is a cell, and it will be same inside at all the points, since we know that the potential inside the cell is constant. Now once we have the potential of this cell, so by applying the formula of capacitance, we can find out the value that is charge by V. The value of V is K times Q by A. So I will write the value of K here, that is 1 by 4 pi epsilon naught, and this Q will cancel out, so you will get 4 pi epsilon naught K. And as you can see from this equation too, that 4 pi epsilon naught is a constant quantity, so the capacitance of this cell only depends on the radius of this cell, not on the charge of the cell. And this was told in the previous lecture also, that capacitance of a body is independent of the charge on it. So we can clearly say that if I am going to increase the radius of this cell, the capacitance is going to increase. Now I am just going to discuss a case when two oppositively charged plates are placed close to each other. So if I am having two plates that are little thick and they are oppositively charged. So as we know that opposite charges attracts each other, so the most part of the charge will be on the opposing faces of these sheets. As I told you that opposite charges attract each other, but there will be some charge on the outer surface too. So if I will place two thick plates close to each other, and if I will provide an equal and opposite charge on it, then the distribution of charge will take place like this. If I am interested in drawing the field, then inside the region, the electric field lines will be from positive plate towards negative plate, and we know that at these ends are sharp, so the density of the charge here and here will be more. This has been already told to you earlier. Due to this accumulation of charge at the edges, the field will not be uniform here, and the field lines will be something like this. And on the opposite faces, definitely as the lines are perpendicular to the surface, so these will be the directions of field lines. Now, due to these charges, there is some spreading, or you can say fringing of field at the corners. But if I will take a sheet of very large area, then most of the charge on the plates only resides inside the facing plates, and there is a minimum fringing except the edges. So if I will take large conducting thick sheets positively charged, and if I will place it close to each other, then generally we can assume that the electric field between the plates is almost uniform. The simplest form of capacitor is two parallel plates separated with a small distance. Like this, we are having two plates, conducting plates. If I will place these two parallel with a short distance, then this is the simplest form of capacitor, and this is called parallel plate capacitor. So we have two parallel plates separated by a distance d, and that is small in comparison to the dimension of these two plates. And as I told you that one is charged positively and other is negatively, so if the plates are given charge, then most of the field, electric field, will localized between the plates of this capacitor. And suppose that this is my plate P, this is my plate Q, so the field will be almost uniform. It will be better if I will draw a side view of this. So you have these two plates P and Q, and they are separated by a distance d, that is very small. The area of each plate is AC, and these are the wires. If I will provide the charge, then it will uniformly distribute as we have discussed, and most of the field will localize between the plates, and this field will be uniform. If these are two plates, so in presence of charges on the plates, a potential difference, say VPQ, will set up between the plates, and such an arrangement is called parallel plate capacitor. We have worked out the field due to a charged sheet in the applications of Gauss theorem. So with that idea, suppose that there is a point here in the space between these two plates. So due to this positively charged plate, the electric field will be away, and for this negatively charged plate, the field will be towards this place. So the contribution of both the plates for the electric field is in the same direction. So I can add these two fields, that is the electric field due to plate P and the electric field due to plate Q. And as we know from Gauss theorem that field due to a charged sheet is sigma by twice epsilon naught, and the same will be due to this plate too. So on simplifying, we will get electric field as sigma by epsilon naught. If I will place the value of charge density, since we know that if the charge is known, that is Q say, and area is known, so we can easily find out the charge density as charge divided by area. So electric field will be Q by A epsilon naught. Since the field is known between the plates, I can easily calculate the potential difference between the plates, and that is with the relation of electric field with the potential, and that says that potential difference is electric field multiplied by the separation. So with this we can find out the potential as QB by A epsilon naught, and once we know the potential difference, we have the capacitance as charge divided by potential difference. So if I will put the value here from this equation, this is QB by A epsilon naught, which on simplifying gives A epsilon naught by D. And that is very clear from here that capacitance is proportional to the area of the plates, and it is inversely proportional to the separation between the plates, and that was discussed in the previous class also, that if I will reduce the separation between the plates, definitely the capacitance will increase, and it will also increase on increasing the area of the plates. So this was the capacitance for such kind of configuration, and that is called parallel plate capacitor. Now, since we have the formula for the capacitance of parallel plate capacitor, so let us do an activity. Suppose I just wanted to make a parallel plate capacitor of capacitance only 1 farad, and I am generally taking that I will separate the plates of my capacitor whose capacity is 1 farad by 1 mm. So my task is to calculate the area to manufacture such kind of parallel plate capacitor. So let us execute this activity. So I am having a capacitor, the separation between the plates is 1 mm, and I need that its capacitance should be 1.0 farad, and I need to calculate the area for such kind of capacitor. So we have the formula of capacitance as A epsilon naught by D. So if I need A, simply I have to put the values of all these that is known to us. Capacitance is 1 farad, separation is 1 mm, so I will convert it into SI unit, and divided by epsilon naught, its value is near about 8.85, and this for minus 12 SI units. And if you will simplify this, you will get A equals 1.1 into 10 raised to power 8 meters square. Just look at the area for such a 1.0, only 1.0 farad capacitor, and the plates are 1 mm apart, and the area comes out to be 1.1 into 10 raised to power 8 meters square, or generally we can say that it is 10 kilometer squares. Just think about the volume of such a capacitor whose each plate is near about 10 kilometer squares, and think about the volume of such a capacitor, and that will be very large. So it is very tough, but in physics nothing is tough. We have the easiest way. We can make a capacitor of this capacity with few centimeters on site. And the trick by which we can do it is an appropriate substance between the plates of a capacitor rather than its volume, so that the value of the separation can be reduced greatly. So if I want to decrease the area, I have to reduce this separation, and that can be done with the help of a dielectric medium inside it. So suppose that I have filled the area with the dielectric of dielectric constant K. So in that case the capacitance would be A epsilon naught K divided by D, and due to insertion of this dielectric substance, the separation can be reduced much more, and consequently the area will be much less in manufacturing of such a small capacitance capacitor. We will explore this idea of introducing the dielectric between the plates of capacitor later on in a detailed way. So we have an idea how to find out the capacitance of a conductor, capacitance of a parallel plate capacitor, and we will utilize this idea to find out the capacitance of a spherical capacitor. For a spherical capacitor, we have two shells, concentric cells with different radii. Consider the radius of this inner one is A and the radius of this outer one cell is B, and these two are charged with plus Q and minus Q charge. So both the plates, I will make it like some more spherical, like this. So these two plates are equal and positively charged, the center is common. So this kind of capacitor is called a spherical capacitor, since we have two spherical cells of different radii with the common center O. And let me call this cell as A and this cell as B. So our first task is to find out the potential difference between these two cells, and we have an idea how to calculate the potential of cells. So first of all, for cell A, the potential due to its own charge is K times the charge divided by radius, and the potential of this cell on this shell. So as this cell is outside and the point is inside, so we know that the contribution of potential due to outer cell will be same as the potential on its surface. So I will write this as K minus of Q and divided by V, because you know that in potential we have to take the charge with proper sign. So this is going to be like KQ 1 by A minus 1 by V. Now to find out the potential of this cell, first we will calculate the potential due to its own, and that will be K times the charge divided by radius, and there will be contribution due to this plate too, as this point on which I am just calculating the potential is outside this cell. So for that we know we will write K times the charge on inner cell, but the separation will be from that center to this point, and that is B, and which gives me zero potential of outer cell. So now the potentials are known, and we can find out potential difference between these two cells. So this will be VA minus VB, and as VB is 0, so it will be the potential. So I can write it like V minus A by AB, and this is the potential difference. Now the capacitance is the ratio of charge to the potential difference. So I will just put the value here, and the value of K we know, this is 1 by 4 pi epsilon naught Q B minus A by AB. So on simplifying we will get 4 pi epsilon naught AB by B minus A. So this is the capacitance of a spherical capacitor. Now just look at the condition, and the condition is that suppose my outer shell is located at infinity. So in that case the B will tends to infinity, and if B will tends to infinity, then if you will apply this condition here, or simply just look at here, if B is corresponding to infinity, then this term will be almost 0, and the final potential at A will become KQ by A. So for this condition, the potential of A will be K times Q by A, and if I will put the value of K, this is going to be 1 by 4 pi epsilon naught Q by A. The potential of B is 0 as we have calculated. So the potential difference is simply this value, and this is 1 by 4 pi epsilon naught Q by, this will be A, Q by A, and in that case, if you find out the capacitance, then it comes out to be 4 pi epsilon naught A. And if you can remember the previous derivation, that it was the capacitance of a spherical conductor. It means we can assume that that spherical conductor is a spherical capacitor with its outer plate at infinity. Now, one important thing, that there is a air between the space of these two cells, and as I told you that if you will fill the space between these two cells with the dielectric constant say K, then my capacitance will become C equals 4 pi epsilon naught K AB by B minus A. Let me write it here. C will be 4 pi epsilon naught K AB by B minus A once you have inserted a dielectric medium of dielectric constant K between the plates of spherical capacitor.